Good morning, ladies and gentlemen. Geospatial imagery is used more and more across industries because it provides up to date, accurate information about any area of interest. Imagery is used to evaluate biodiversity, detect and identify targets, plan emergency response efforts, and many other applications that are important for understanding the world around us. While vast amount of digital satellite and aerial imagery is available, the real challenge is in analysis of the raw image, extraction of useful information with high accuracy, and applying it to the real world decision making applications. To do so, we need advanced software technologies that can effectively exploit the growing number of sensors and increasingly large data sets they provide. Imagery is the foundational data source for information that supports decision making. Organizations are using imagery to support precision mapping and reality capture, to identify spatial patterns that help them understand the natural and built environment like urban growth, crop yield, land cover, habitat loss, and many more. This imagery that we talk about comes in all kinds of format from multiple sensors and modalities. This multispectral imagery that involves acquisition of visible NIR and SWID bands in several wavelengths. Multispectral sensors usually have between 3 to 10 different bands. QuickBird, Spot, Landsat satellites are well-known satellite sensors that use multispectral sensors. Hyperspectral sensors measure energy in narrower and more numerous bands than multispectral sensors. Hyperspectral images can contain as many as 200 continuous spectral bands. The numerous narrow bands of hyperspectral sensors provide a continuous spectral measurement across the entire electromagnetic spectrum and therefore are more sensitive to subtle variations in reflected energy. Talking about the difference between multispectral and hyperspectral, uh, multispectral imagery, if it can be used to map out the forested area, hyperspectral imagery can be used to map the tree species that are available within the forest. Thermal image measures the surface temperature and therefore is being used in study of plant heat stress or detection of urban heat islands or land surface temperature analysis. Few sensor systems operating in thermal IR region are AVHRR, Landsat, ESTA. DEM, as we know, is a representation of bare ground topographic surface and is created from variety of sources. ALOS Pulsar, Aster, SRTM are few of the DEM data sources commonly available for the user. LIDAR, which stands for light detection and ranging, is an active remote sensing method that uses light in form of pulsed laser to measure distance to Earth. Looking at the uses of LIDAR data, is picking up the across diverse fields from building 3D models of buildings to vegetation health to environment science. Drone data is basically the capture of images using RGB or multispectral cameras for cadastral mapping and many other applications. Ground is photographed with these sensors and is used to create geospatial products like orthomosaics, DTM, DEMs, or 3D texture mesh. So, to sum up, there are more than 200 sensors giving us more than 70 raw data set in different formats, including the scientific formats such as NetCDF and HDF. And GIS user needs one solution to read and analyze such data sets. ENVI is a premier image processing software that includes comprehensive suite of image analysis tools which allows user to access proven algorithms to analyze image quickly, easily, and accurately. It supports imagery from today's newest and most popular satellite and airborne sensors, including multispectral, hyperspectral, panchromatic, LIDAR, and many more. And we can work with any size of data set because imagery, as we know, is in bulk and requires huge processing values, and therefore it provides a flexible solution that can be customized to meet specific project needs. Automated workflows help in faster processing and guide the user through processing steps, thereby making it useful for everyone from a GIS professional to image analyst, regardless of the prior experience. So let us quickly look at a very ENVI interface. So this is an ENVI interface where it supports multiple optical sensors from Landsat to ComSat to Airbus. Then this software supports the radar sensors, the thermal sensors, the DEMs like SRTM and ASTERS. It also supports the SARS dataset images from RadarSat to RESAT to Capella. And finally, the scientific formats that are generally used for grain analysis or that comes with sea surface temperatures, those can also be read and ingested directly into the software. So here, as you can see, I have taken a drone image, Megasense image, with 5 multispectral bands, namely blue, green, red, red edge, and NIR. These bands can be used to compute multiple vegetation indices and monitor health of crop to individual plants levels. So we've all seen classifications and different band algebras and indices.
Hello, Manjusha. Sorry to interrupt. Your presentation, if you are showing your demo, it's not visible. You have to share the demo.
It is already, I'll stop sharing and share again.
Yes, yes.
Is it visible?
Yes, Manjusha. Please continue.
Okay. So as I was talking, ENVI supports many different sensors, from optical sensors to radar sensors to digital elevation models, SARscape models, and finally the scientific formats. And these are the toolboxes that helps that has many algorithms depending on the user's requirement that can be used. So this is a Megasense image of 5 multispectral bands, namely blue, green, red, red edge, and NIR. So these bands can be used to compute multiple vegetation indices and monitor crop health to individual plant level. So as can be seen, this is a pumpkin field, and to manually go and monitor and collect each and every sample is a tedious job. Using remote sensing and tools provided with ENVI, I can simply do indice, which is like NDVI or GDVI or many other indices that are available depending on the data set that I have given. So here I have used the GDVI index that has very prominently marked out my pumpkins available in the region. And finally, putting a mask to the to my GDVI output, I can actually see all the pumpkins that are available with me. So counting these crops will become very easy, and if we can see, each and every pumpkin is mapped to the individual plant level without any interference from the background, that is the soil or other vegetation or leaves that are present in the area. So this is the sort of precision agriculture that is needed in today's world for better decision making. Hyperspectral, moving on to studying of the hyperspectral imagery. So hyperspectral remote sensing is based on taking a fraction of electromagnetic spectrum and breaking it into numerous bands for theoretical analysis and computation. But a hyperspectral, the main requirement of hyperspectral image is the processing. It requires extensive pre-processing so that it can provide us with the useful spectral information. Calibration, noise, bands removal, atmospheric correction, all needs to be done for a hyperspectral spectral analysis. So ENVI provides a set of tools that can be seen on the right side, which can be used to do the pre-processing and analyze the data, build a spectral library out of it, and help or target or identify the available target. So let me quickly show how we can work with hyperspectral imagery in ENVI. So this is hyperspectral imagery of Everest. So as can be seen, there are some 224 bands. The exclamation marks along with the band means that these may be noise, these may be bad bands, or these may not have been identified. And also working with some 200 bands is not very feasible for the user. So using the process of MNF, that is the noise removal process, and doing a pixel purity index, ENVI can do a pixel purity, or can reduce these numbers to some 179 bands that are actually used for the analysis. So a simple hourglass or a simple step-by-step automated process that can be used is ENVI hourglass. So this hourglass actually is a wizard that process or uses the spectrally overdetermined nature of hyperspectral data and find the most spectrally pure and spectrally unique pixels and within the data set and map their locations and subpixel abundances. So this processing or this flow begins with the reflectance and radiance input, as I've shown. So we can spectrally and spatially subset the data set, visualize the data in ND space, that is the 3D space in which we can identify or target our pixels. So this is a step-by-step process. The user can only tweak the parameters that are available, else the software gives the best parameters that needs to be taken care. If a user, so once all these are done, we have a final classification classification by comparing it to the spectral libraries that are available to us. So this classification is finally computed in, say, soybean, wheat, corn, and different classes that was available, say, water. Also, so these the application of such hyperspectral images are basically in vegetation where there are narrow bands that needs to be monitored, and there are light canopy or canopy bands that needs to be monitored for a good vegetation. So sometimes the weeds or the pest and other problems or other we can say agricultural calamities can occur, which can be actually monitored using the vegetation index calculator provided. So this is a thorough tool wherein from the anthocyanine to carotenoids to the nitrogen content that is available with the data set or the canopy water content can all be monitored in one toolbox or a wizard and can be seen. And depending on the user's requirement, the user can actually identify his or her own index that he wants to further analyze and can take it. And also this shows agricultural stress vegetation index. So this agricultural stress can be basically divided into 9 different categories. For one, it shows a low stress. For 9, it shows a maximum stress in the agriculture farm. So these type of analysis is also possible using hyperspectral imagery in ENVI. So some of the hyperspectral sensors that are available in today's scenario is satellite-based, airplane-based, and UAV-based. So HISIS, so Hyperion data was initially there, but it is not working anymore. But we have the Everest, we have the Prisma data that is really available and is supported by ENVI. So now working with the DEMs, the DEM is generally, as we know, is used for extracting the terrain parameters for geomorphological studies and hydrological modelings and many more. So for DEM, the ENVI provide general tools that can be used for analysis of such topographic data set. A variety of DEM specific tools are also provided for processing digital elevation data. to generate geomorphic measures such as slope, aspect, shaded relief, profile convexity, plant convexity, and many more. And we also provides a comprehensive capabilities for viewing and analyzing image data in 2 dimensions. The ENVI 3D surface view tool is the first step towards extending these capabilities into 3 dimensions. ENVI 3-dimension surface viewing function allows the display of DEM as a wireframe, rule grid, or points, or grayscale, or color image draped over it. The 3D surface can be rotated, translated, and zoomed in or out in real time using the mouse cursor. Each of the 3D view can be added to the list to be used later for animation. A fly-through of 3D dimensional dataset is achieved using the saved view or a predefined flight path drawn interactively using the ENVI annotation tool. The vertical exaggeration, vertical and horizontal view angles and altitude are controlled via user selected parameters. The cursor is also linked to drape 3D image, allowing extraction of profiles in X, Y, and spectral directions, as well as cursor locations and value utilizing the 3D projection. So let us quickly see how the EM can be used in ENVI. So this is my normal Aster DEM that I've used for an area. So using my 3D surface and using the my multispectral image, that is supposing sphere band, NIR, and the red band. I'll leave the rest of the parameters at default. Depending on the user requirement, he or she can give a minimum plot levels of DEMs. He can give vertical exaggerations and the resolution also at which he wants to see the DEM. So once this is done, this is how a 3D view of the area looks like. So as we can see, we have a terrain terrain area that is basically covered with ice, which is not very much visible. This can be is visible only when we have draped our multispectral imagery onto the terrain model. So as I was talking, using the surface controls and motion controls, position controls, we can further analyze this model in 3D shape and size. So also the main aspect of 3D modeling is to get the slope, aspect, shaded relief. So instead of going one by one process, this the tool, basically the ENVI, allows the user to calculate compute all of these topographic data or topographic products and give it as one go to the user. So the user can then take out whatever is necessary and can further analyze the data set. So supposing if I want using this product, if I need to only look at the slope of the area, I can do so. Or if I want to see the whole shaded relief, that can also be done. Finally, for a terrain analysis, a viewshed analysis is the main purpose. So a viewshed analysis can be easily done by giving a simple DEM file and a multispectral file that is completely optional. And once I've done the same, the wizard will allow me to give the default range for which I want to see the view with my view shed, and a minimum height at which I want to see, and a default spacing. Using my pencil, or if we have the point of interest already with us, we can give the ROIs, or else using the tool I can also give any data point at which I want to see the viewshed analysis. So it will quickly generate a viewshed for me, wherein the red area will show the areas that are not visible, and the green ones will show the areas that are visible. So we can simply export these data set and can take it to any platform and work further with it. So for any one area, This is how we actually extract the viewshed data or results, that where we know that yes, as I've already said, green represents the visible and red represents the invisible or not visible area of terrain. Um, so now, next is the processing of the SAR data. So SAR, as we know, is bounces the microwave radar signals of the Earth's surface to detect physical properties. So the measure of the backscatter is due to the roughness of the surface, helps us to differentiate different features of the Earth, such as smooth water body with low roughness, or show a less less vegetation in vegetation area. So a basic difference between optical and SAR, as can be seen here, is towards the left, we have the dark fields or the dark areas. If we compare the optical and the SAR, so the SAR would show a dark field, because the ground is wet or it has moisture in it, and the brighter pixels is maybe because the crop is growing, or and there is a lot of backscatter. So a typical difference between optical and SAR would be the optical operates in the visible and infrared bands of the electromagnetic spectrum, while the SAR works on the microwave. Optical is a daylight sensor, while SAR operates on both in both day and night. And the SAR can also penetrate through cloud, which makes it very useful during the monsoon season or cloudy season in case of agricultural applications. So radar band frequencies, as we know, is basically the L, P, X, C bands. These are the different type of bands that are available with the sensors today. So L and P band have longer wavelength and are dominated by soil backscatter. They are used mainly for soil moisture and information on thicker vegetation, while C and X band interact mainly with the canopy. X band works well with the broad-leaved plants, for example, say corn and soybean, while the X and C works well with narrow-leaved plants such as grain. So ENVI provides a complete and exhaustive set of tools to work with SARS. So if a person has a good knowledge of the SAR system and knows the technique behind it and what the whole algorithm that goes behind the processing of a SAR data, he or she can use the SARscape module that gives a comprehensive tools and wizards to work with the same. But somehow if a user doesn't is not very, or has I can say a basic knowledge of SAR and doesn't know much about it, he or she can also work with the SAR using the SARscape analytic tools. So the SAR analytic toolbox, as I was mentioning, is basically used for users. That is the flood mapping who wants to do a change detection or a simple DEM extraction. So the SAR time series analysis or a ship detection. These are simple tools or wizards that can be used for SAR analytic toolbox. So let me show a simple demo for the same. So a simple now, as we know that SAR requires a complete processing, a pre-processing for the information to be extracted from a SAR data. So initially using the intensity time series, we give an input, we do a multi-looking, this co-registration, speckle filter, noise removal, and all these steps are taken care of in this one intensity time series tool wizard, and we get a final output using the same. So if we see the output of the data set is right in front of you. So these are all some colored pixels that are available. So in order to identify a pixel and know how the spectral signatures look like, we need to plot these and get a plot. So as you can see, I have identified water that has a low backscatter and is therefore can be seen at the bottom of the plot, while built up area shows a maximum backscatter and is therefore on the top of the uh, plot area. While there are crops that shows a very significant and very continuous and similar pattern and can be classified. So using these data set and the various statistical products that have come out from these analysis, so covariance, standard means, average backplotter. So using all these in our output, we can actually define a decision tree that help us to basically extract the bodies, the classes that are available. So here, as we can see, I've only if a person wants to know exactly the built-up area around the around his or her locality, he or she can do so using the SAR analysis as well. Next, LIDAR. So LIDAR, as we know, is a light detection and ranging method that is generally used for in finding usage in many domains such as geological studies on forestry, agriculture, disaster response, and even archaeology. So ENVI LIDAR has some processing capabilities that are accessible directly through the graphical user interface. So a user can easily create a DEM, extract buildings, trees, power lines, and power poles from the dataset. So let me also show you how LIDAR dataset can be used in using ENVI. So once we have the data set, that is a LAS file into our software, the user has the liberty to pick any or produce any feature he or she wants. He can produce a DEM, trees, building, PowerPoints, and can also give the parameters or tweak the parameters for the same and can get the output result. So for one area, for a small area, I've already created a DSM. This is the terrain model wherein I've extracted the building, trees. So trees, depending on the parameter that I've given, it has identified even the trees that have minimum height of say 5 to 10 5 to 10 centimeters or meters. Then it has also given me some power lines and can also generate a DEM contour. So this is just one application. This is a simple out-of-box, ready-to-use toolbox that is available. A user, if he wants, he can also use the API or ENVI API or ideals to further customize his working with LIDAR dataset. So moving on, ENVI modeler. So the data set, the working of working with imagery is nowadays not limited to just one data set. So supposing if a person wants to use both SAR and an optical image in his or her analysis, he or she can do so using the ENVI modeler by creating a simple workflow. So for this, we don't need any coding. There's no programming required here. The user just needs to drag and drop the tool boxes and can build his, and giving the parameters that are required, he or she can build his own workflow for the same. So here, as can be seen, the SAR data processing and the Sentinel data, basically 1 and Sentinel-2 are both fused together for an application in ENVI modeler to get the desired output. Also, ENVI is deeply integrated with ArcGIS. So whatever outputs that are created within the ENVI can directly be taken to ArcGIS and can basically the user can modify his or her own data accordingly. So if a user has built a workflow in ENVI, like it is shown in the bottom, so he or she can take it to Arc directly, and the user need not do the same work again and again to provide the same. And also the output results that are available can be directly ingested into. So supposing if a user has worked with, say, some different data set, say ALOS or Prisma or some other data set in ENVI, there are tools that are available that can be directly into ArcPro, and the user need not go for the ENVI GUI to work with the same. So with this, I conclude.